All right. My name is Bryan Clapper. I work for Databricks. If you happen to be at Scala I/O a couple of weeks ago, this is pretty much the same talk I gave there. In fact, they gave me 50 minutes. I have 40 minutes here, and I haven't cut any content. So we're going to see if I can do 100% of the content in 80% of the time. So let's put your seatbelts on. Let's see what happens. Despite the fact that we're talking about frameless in here to some degree, there's no category theory in here, so if that's what you're expecting, I apologize. Frameless does use a lot of type-level programming, but mostly this is about using the APIs, not how are they programmed. If you want to talk more about how they're programmed, there's a young man sitting right here who can help you. Raise your hand, Long. So basically, if you don't know anything about Apache Spark, hopefully you'll walk away with an understanding of Spark at the end of this talk, at least an initial one. What the intent here is to compare and contrast the standard Spark data frames and datasets APIs with the type-level Frameless API. Now, this is exactly what one of the pages in the Git book that Frameless publishes does, but I'm going to do it in a slightly different way. And in fact, I'm going to do it live coding, mostly in a Databricks notebook. So we're not going to be looking at a lot of slides, and these notebooks are actually out there for you to load up and use if you want. I'll walk through that really quickly. So again, as I said, it's oriented more toward learning how to use these things than how are they actually implemented, though I will talk about some tuning measures and things like that under the covers. All right, and hopefully at the end, as I said, you'll walk away with some understanding of Spark if you don't already know it, and you'll have some idea of how Frameless compares to the native APIs. And so this is the last slide. This is not slide-oriented. There's a GitHub link here, but if you forget that really, really long URL, that's fine. Just go out to my GitHub repo. BMC is really easy to remember, and I've pinned it. Okay, so it's actually pinned out there, and you can go find that repo pretty quickly, and the notebooks are out there. The README instructs you as to how to load them up. And of course, if you have questions, you can just send me an email and say, hey, what you wrote makes no sense. Can you tell me how to do this? So all the code is available for you to look at if you want, and the data is available. You can download your own copy of it. So let's, with that said, let me pop over here. First notebook that I've got is one that I'm not going to go through, but this one is in the set of notebooks, and this is how you go get the data. Basically, I have a Scala server out there that reads from the Twitter fire hose, which is appropriate given where we are. That wasn't planned. And then dumps it into, reads a certain amount of that data down and then dumps it into a Parquet file for analysis. So you can create your own copy of that file by just running the stuff that's in here. And then there's another file that I pull down only for doing a join against as a demo. That's Twitter data from like February. So we can do a quick historical analysis. And it's mostly just an artifact I can join against. So you run through this notebook. It has explanations as to how to get the data down and where you can pull it from. So if you want to run this yourself, that's what that's for. Where we're going to be spending our time is in here. So I walk to the back. I can read this with my trifocal, so you guys should not have any complaints. But if you can't read it, raise your hand. I'll make it bigger. So let's just dive right in. That's my 3-minute intro, so I should be able to fit this in the remaining 37 minutes. So the first thing we're going to look at is the data frame API. Okay, so you may have heard of the RDD API. This is the older API in Spark that looks almost exactly like the Scholar Collections API, and that's not what you should start with these days. I mean, there are arguments for using the RDD API, but you should always start at the higher level with the data frame or Spark SQL APIs because you're going to get better performance. Right, and we're going to talk about that a little bit. But one of the things you don't get is the kind of type safety you want, which is sort of the focus of this talk. So what's the data frame API? And I've already primed this a little bit. I've got some shared defs here. This just runs another notebook to set some stuff up. And I've already loaded this guy up. So there's my file full of tweets. I ran this morning. It has about, as you can see here, it has about 50,000 and change tweets. And again, this is sampling, right? It's the Twitter API that they're not giving me everything, but it's relatively up to date. So here are some of the things that we're seeing. So the data frame API is a DSL, so it implements a query language. It looks a lot like SQL, at the programmatic level. In fact, you could actually substitute SQL here using the Spark SQL API, and it would work exactly the same way. And it's about as type safe as SQL as well. So here, what I'm going to do is I'm going to select. You can see up here that the hashtags column is actually an array, right? So what I'm going to do down here is explode this so that this particular row has 4 hashtags in it. What I'm going to get when I explode it is 4 rows with all the data duplicated, but a different hashtag in each row. Okay, so it's like a pivot. So that's relatively easy. I'm caching it just to make the performance a little bit better. We're going to select an explosion of that, and we're going to call it tag. And then we're going to group by the lowercase version of the tag. Okay, looks like SQL, right? We're going to count the number of tags. How many of each tag do we have? And then we're going to sort in descending order so I can see what the most popular tags are. And this display function is a Databricks specific function. With normal Spark, you would just use .show, but you get sort of an ASCII display. Here I get something a little easier to read. And I have no idea what half of these things mean. Does anybody know what Daddy's Girl on Fire means? I have no freaking clue, but that's the most popular hashtag at the moment, apparently. So, you know, the query language is reasonably powerful. And as I said, it's quite reminiscent of SQL, which is deliberate. So let's take a look at some hashtags we're guaranteed to be there. No matter what is going on, given the current political climate, pretty sure I'm going to find some tweets that match these hashtags, right? Now note that in order to cover upper and lower case in here, I have to actually spell it differently. It's actually remarkably difficult to do the kind of transformation I want to do within this array contains function. So this is kind of ugly, right? We can get around this a little bit later when I talk about data sets. Right, so here we're going to select these tags, and we're going to actually filter out so that I'm only getting tweets with these 4 tags, and then I'm only going to select these 4 or 5 columns out of the data frame, out of all the columns that we get. So how many did we get? Well, there are 27 tweets from the 50,000 or so that use one of these tags, and if I display them, you can see what we've got, right? Oh, look, QAnon shows up right away. Isn't that special? Okay, so I'm not going to actually look into this. It'll probably just piss me off. So let's take a look at the schema for the data frame. Okay, so this is the original data frame. Up here, what's really happening is this is kind of lazy. So tags is really just another data frame, right? So applying these transformations, the filter operation returns a data frame, which I'm not storing anywhere, right? It's transient. And then the select operation returns another data frame. These are all lazy. Really what's happening under the covers is each of these transformations is adding to a query under the covers. So you're building up this query AST. You could even throw SQL in here in the middle and it would just add to this query AST. And then eventually when I run what's known as an action, and display is an action, right? Display says you got to go out and actually read the data now and then pull it back so I can look at it. That's an action. That actually kicks the job off and distributes it across the cluster, causes the calculation to occur, and then pulls the data back. Right, so really briefly, I'm not going to go too much into Spark architecture, but really briefly, think of there being 2 components here. There's what's known as the driver. That's the thing that's running my code here. And then when you bring up your Spark job, the driver gets allocated within the cluster executors. These are other JVMs. Typically one per node in your cluster as a typical arrangement. And those executors that come up are dedicated to that driver. So your Spark program actually runs in a combination of JVMs. There's the driver, which you can think of as the orchestrator, and then these executors that are out there. And what the driver does is when you kick an action off, it says, okay, time to read the data. We're going to do this thing. Let's break that data up into pieces, okay, called partitions. And I'm going to assign some subset of the partitions to each of those executors. And then they're going to process those partitions in parallel. So that's the first level of parallelism. You've got 3 or 4 or 8 or however many individual nodes out there with executors. And then within each executor, you also have a thread pool. So that's your second level of parallelism, right? And what will happen is that an executor says, okay, I've got these 30 partitions. I've got 8 threads, let's say, in my thread pool. That means I can try to process 8 of these partitions at a time. And then it will iterate through those partitions. A thread will be allocated a partition. It will process that partition start to finish until it hits something that causes it to stop. Spark calls that a stage. A stage might be, okay, we're completely done with this, it's time to write it out, right? Or a stage could be, okay, I've reached a point where I now have to share this data across the network. Good example of that is a sort or a group by, right? So now we've got to move this data around the network. So that thread will run up to that point and then stop and say, okay, I'm ready for the next partition. So that's the thumbnail sketch of the parallelism in Spark. And so that's what's happening in here. So so this is the original data frame, and notice that this is a schema. I mean, it kind of looks like a SQL schema, and we can see that the first column, in fact, is an array. We can see that this one is actually a struct. You could imagine reading this in as JSON, which in fact it is originally, and this thing contains sub elements. So I could say place.name and pull out some of the location information. Here's the problem with data frames. Here's why Scala people hate them. They're not type safe. So the timestamp column is a SQL timestamp. You'll notice the schema here says it's a timestamp. This corresponds to java.sql.timestamp. Okay, so this makes no sense, right? Really, you can't really multiply a Java SQL timestamp by 1,000. This will fail, but it fails at compile time, or runtime, not compile time. Right now, if you're running inside a REPL like this, you don't really care that it's failing at runtime. But if you're actually compiling your code and preparing it to deploy, you would really prefer that this be caught by the compiler or by Circle CI or Travis or whatever you're running. And that wouldn't happen. You'd have to actually try to run it. So this is actually, you can see it's runtime because you get this lovely, obnoxious stack trace. Right? It's actually worse than that. Sometimes you don't even get an error. What does it mean to compare the user column, which is a string, to 10? I don't know, but it works. So why does this work? This is ridiculous. Okay.
Some definition of work.
Well, it doesn't bail. Okay. But all right. And this is even worse. What does it mean to divide it by 100? I don't know, but what do you get out of it? You get null. Okay. So this kind of sucks, right? I have no protection here against doing something ridiculous, and this is clearly ridiculous. So. And then there's also this, what if I select a column that doesn't exist? That's a runtime error, all right? I don't get that at compile time. I have no protection. The compiler can't help me. So of course, Scala people hate this. So, and then it's worse than that, right? Because even if you get everything right, now collect is an action. So I'm gonna take the tags. Remember this whittled it down to 5 columns. I'm gonna pull this stuff back. Now what I pull back, let's take a look at this. So this is, each collect is pulling back rows. So I've got an array, effectively, of row objects. But the problem is, what is a row object? It's a heterogeneous collection. Okay, first type is int, second type is. So what do these things look like to the compiler? Well, let's assign it to a variable, and you will see. It's any. So now if you want to do something useful with it after you pull the data back, you either have to do stuff like this. This should look remarkably like JDBC, the API we all love to hate. Right? So you have to cast using these built-in things, or you have to literally do an as instance of to pull this back and make something meaningful, back in the driver. And of course, if you get it wrong, you're going to get a runtime error, not a compile time error, because it's a cast. All right, so one way you can get around this is to use something called the dataset API. So what's the dataset API? Well, so let's take our schema and recast it as some case classes. And that's a reasonable layout for it. Okay, these are type-safe versions of the schema. So what I can do is take my data frame and cast it. Now I'll get a runtime error here if I've chosen case classes that don't match up. So what do I mean by match up? What's going to happen is there's a certain amount of reflection going on here, and Spark is going to look at the columns and match them up by name to the values in the case class, the fields in the case class. And it's also going to verify that the types work properly. And this is exactly a cast. If I screw this up, and I'll show you that. Here's one where it's bad. Okay, so these are wrong types. This is the wrong type. Okay, and if I try to do this cast, notice I'm getting, again, a runtime error. But once I get past this runtime error, I've got this data set. So I'm going to quickly throw this in here. Let's take a look at the type. Note that the type now is data set of tweet data. It's no longer data set of row. So now this thing has a type that the compiler can actually help me with. Nevertheless, I can still use the traditional query API against this if I want. Okay, I can treat this the same way I operate on a data frame. And in fact, in Scala, a data frame is nothing more than a data set of type row. It's a type def. It's just a data set with not a very useful type. So I haven't changed anything here. I would still get a runtime error here if I gave it the wrong column. Okay, so I'm still not getting any compiler help with the query API. But where I can start to get compiler help is by doing stuff like this. Here's a traditional filter, right? This looks like the kind of thing you would use with the collections API. And so now I can say, look, I'd like to look at only the rows that have hashtags. So hashtags non-empty. Boom, this works perfectly, right? And now, if I change this to the wrong thing, I'm going to get a compiler error, of course, because it knows the type. Should probably kill those lights if we can. Right? And if I display this, this is where we solved that problem from before, right? Where now I can actually do it to lower here. So I don't have to have 5 different array contains. I can just do the one thing here. So great, we have our types back, right? Isn't this great? Now the compiler can protect us. You know, now if I try to do a comparison of timestamp, you know, I get compiler errors. If I try to multiply it by 1,000, I get compiler errors. And when I collect the data back, I actually get back data in something that is useful to me. It's an array of tweet data, no more casting. I did my cast up above, but now I've got my types back. This is awesome, right? So why don't just stop here? Why do we have to talk about Frameless? We can stop here, right? This is great. We're done. We're not done. Data sets have problems. Okay, there are a couple of problems with data sets. Problem number 1 is tungsten data format. Anyone in here hear of that? A couple of people. All right. So when you're operating at the data frame level, the Spark SQL level, the data that's read in, when it reads the data out of these partitions into memory, it reads it into this compact Spark optimized serialized format called tungsten. Now, contrast this with the old RDD API. The old RDD API was programmed entirely with lambdas, right? And so the way that the data was read in, it was read into literally an RDD models an array of some type. So if you read a text file in, your first RDD is an RDD, an array of strings, right? A distributed array of strings. Each of those strings is a JVM object, right? Because you need to have an object so you can pass it to a lambda, right? You can't pass something weird to a lambda, you got to pass an object in. This means that that entire partition, every column in that partition has object overhead and is also subject to garbage collection. Tungsten doesn't do that. It's very, very compact. It's actually optimized for common Spark SQL operations like sorts and order by. In a lot of cases, the query, when the query is actually compiled down to the underlying internal RDDs we don't get to use, they can operate directly out of tungsten. So they don't have to actually deserialize and then reserialize this data. When they do have to reserialize and deserialize it, it's orders of magnitude faster than, say, Cryo or the standard Java serialization. And it's not subject to garbage collection. And it's much more compact. So you save memory, you're not paying GC penalty, and it's quite efficient, right? What do you suppose happens up here when I add a filter operation to a data set? My filters are getting a JVM object, right? I'm not operating out of tungsten, so something is going to have to manifest an object for me. What Spark actually does under the covers is it says, oh, you've got this object going into this filter operation. So it actually writes Java code specific to how to decode tungsten into my object. And then at the other end of my pipeline of Lambda operations, it re-encodes it, writing on-the-fly code. Right? One of the guys in, Michael Armbrust, one of the guys in the engineering team, described it like this. What if you gave a first-year computer science student the task of taking this, serializing this case class? What would that first-year computer science student do? It will probably come back with something that's very, very specific to that case class. You can't generalize this. But because it's specific to that particular data type, you can now optimize it for that data type, right? And their realization was, hey, maybe we can implement that first-year computer science student in Spark. So they do. They write Java code under the covers, and they use Janino to compile it on the fly. But there's still a penalty, right? You've got to actually run that code for every row that you're piping into that filter operation. And then you got to re-encode it on the other side. So you're paying a performance penalty. Now, it might be okay if you're running a job late at night, you're not around to watch it, and this is going to make life easier for you, but you need to know there's a performance penalty associated with this. You've got to deserialize the data out of tungsten into objects, and then reserialize it back into tungsten when you're done. So your type safety here comes at a cost. Another cost is right here. So let's take a look at this operation. We've got a filter operation here. I'm filtering on a user. Now that's a data frame. Then I'm going to cast it to my type, my tweet data type. I'm going to do another filter using the data frame API, right? Then I'm going to do this red here. I'm going to do a filter and a map operation using a Lambda. And then I'm going to go back to a data frame and write it out to a CSV file. Now, the interesting thing here is that Spark, those first two filter operations could be combined into one operation. And Spark can actually do that because it's a DSL. I'm giving it all the information it needs. It knows I'm operating on the text and user columns. It knows I'm doing a comparison, either a like or an equivalence comparison. It knows the literal or the string that I'm comparing it against, right? That's all part of the query. And it can actually optimize that, and it can say, let's combine those filters. Or if I happen to be querying something like an RDBMS, it can actually shove those filter operations down into the RDBMS so the data doesn't even manifest. Hey, the RDBMS is capable of doing a where clause. Let me shove it down in there. But as soon as I hit this filter, it doesn't know what's going on in there. That's code. That's bytecode by the time Spark sees it. It can't decompile that code and figure out, oh, you're operating on the hashtags column and you're calling the equivalent of lower, and I could rearrange this. It can't do that. It can't do any of those optimizations. And I can actually demonstrate this, right? So this is, so here's an example of one. We're gonna actually load up this. Remember I told you I have this historical data out there. And what we're gonna do is we're gonna read up that historical data. We're gonna select just the screen name, right? And I'm gonna union that screen name with the screen name from my existing data frame. And I'm going to write it all out, right? In fact, we could get rid of the union here. And let's just write this all out. Okay, and what we're going to do is we're basically getting all the users who were tweeting back in February. And then we're going to see, are any of those users still tweeting these MAGA hashtags, like 8 months later, 9 months later, right? So while that's running, so here's my join, right? So we're going to read up the users from the historical stuff, and we're going to do this join. Now, if you look at this join, it's kind of inefficient if you were to execute it as it's written. Because it's doing a join, it's joining the most users thing against the tags data frame, which is this winnowed down MAGA tags data frame that I created earlier. And then it's doing a filter to filter out, I'm looking for that particular user. That's probably not the right user now, it's probably different data, but you get the idea here, right? So here's the join, and if you look at this, that filter's in the wrong place. Wouldn't you rather, I'm filtering one half of the join. It makes more sense to filter that before I do the join, right? If I filter it after I do the join, I've joined a huge amount of data together only to get rid of half of it. So I should really do the filter ahead of time, but that's okay, Spark does that for me. And if you analyze this, you can actually see that it moved the filter, right? So let's see if we can find it there. There's the array contains, that's the first filter from the tag, number 1 there. But it actually moves the filter object, or the filter on, here it is. There's the filter here. It happens before the join, right? So the join is actually done at step 5. It's moved this filter to step 3. Automatically, never mind what order I put it in. But if I did that filter with a Lambda, it couldn't move it, right? Because it wouldn't know what it's doing. And that's what you can see down here, is that if I do the same thing down here, but I do the filter based on using a Lambda, you'll notice that the filter is the very last thing that gets applied. It's up top now. That's the function apply. So this is a downside of using Lambdas. Spark can't optimize anything for you. Now you got to go back to being very careful again. So datasets gives us back our type safety, but we lose a fair amount of stuff. We lose performance because of the translation, the deserialization, and the reserialization into our lambdas, and we lose the ability for the Catalyst optimizer, that's the name of the optimizer that optimizes your query. It doesn't know what you're doing in the lambda, so it can't move anything around, so it can't protect you from yourself. So this really kind of means data frames are sort of better for you in that regard. Stick with the query API, and the type safety, again, comes at a cost. So this gives us what we now have to step into, and I've got 15 minutes to go through this. So let's see if we can do this. Frameless and typed data set. Okay, so this is really interesting because what's going on here is that Frameless gives us back our type safety, and there are some costs. There's a little clunky usability here and there, but we get back compile time type safety. But what Frameless actually does is it gives us our protection, and yet it still generates optimal data frame code under the covers as, through type trickery. Right, so let's pull in the bazillion imports that we need. And it's really easy to create one of these. I already have this data set, so I just use the Frameless typed data set create function to create myself a typed data set, and it failed. So why did this fail? After a while, you begin to be able to read these things, but it's telling me there's something in tweet data I don't know how to encode. So it uses these encoders to try to figure out, to try to infer the right, the right types to use from your case class. So it's looking at the case class and trying to figure out how do I get the data in and out of these native types here. And there's something missing in the tweet data here. And how do I know which one it is? Well, if we go all the way back here to tweet data, this is the only problem with these notebooks, is trying to find stuff in them. Okay, let's go back. It's up here somewhere, isn't it? There we go. All right, so if you look at all these things, how do I know which one of these things is failing? Well, I'm going to take an educated guess that the likelihood is it's the timestamp, right? Because everything else is a primitive or a string, and it's likely that Frameless has already provided encoders for longs and strings. So let's assume it's timestamp that we're looking at. So let's look for typed data set again. So I take that guess, and you can just use the docs. You basically just have to create this thing that Frameless calls an injection, right? And it's trivial to create this thing. I'm going to create an apply method that will go from a timestamp to a long, a primitive type it already knows how to handle, and an invert method that knows how to go backwards. Okay, so that's pretty straightforward. And there's actually a fairly lighter weight version that you can use in most cases. This is just lambda driven. Okay, so pick which one you find more readable is basically the bottom line. So we'll stick with one of them here. And as soon as I've provided this implicit, this injection, now it will work. Okay, so lesson number one is if you get that error, you're going to have to go back and look at your type and try to figure out which of the types in there aren't likely to have an injector automatically for them, but they're easy to create. So you just create them until the error goes away, basically. Okay, so now we get down here, and the syntax changes a little bit here. I'm using symbols, and I have to subscript the typed data set. Now, by the way, this syntax is very, very similar to what you can already do with the data frame API. I use that $interpolator, but you can also just use the subscripting notation with the data frame API. So it models the data frame API here. And as you would expect, it's a transformation, and it's lazy. I get back another Frameless typed data set with a weird looking schema. Okay, so let's call an action. So in action, I'm going to use show here instead of display. This is more Spark-like. Okay, and normally if I were to use a data frame and I call show, that's going to trigger a job. Huh, that's lazy. Okay, so why is that lazy? Well, because this is type level, right? We actually have to do run or run unsafe or whatever the equivalent is in this API. So what really gets returned by actions here is something known as a frameless job. And I'll talk briefly about those in a little bit, but the interesting thing about these frameless jobs is that like regular transformations, they're composable. So it's really kind of interesting. You can actually create these jobs and compose them later, and I'll talk about that in a little bit. So it actually turns out that even though this doesn't model what Spark does, where an action actually triggers the job, we actually have to call run, it's kind of cool because all of these actions give you back these jobs which you can then meld together, like a lot of the way you might meld futures together or put tries together. So it's kind of interesting. So you notice here when I add the run, I get this output, okay? And let's check the type safety. So I'm going to misspell timestamp here in this symbol, and now I get a compiler error. No, I'm sorry, I get a runtime error because I'm not actually using a typed data set. So this is, I just wanted to show that you can use the symbol notation with data sets and data frames too. So here, again, we're getting a runtime error because this is the standard data frame API on a data set. If I do the exact same thing here slightly differently, now I get a compiler error. So now I got my types back, right? I've got my type safety back. There are various column operations. Almost all the operations that you will find in the data set or data frame API, you can find in the typed data set API. So here we're going to say, I want to select the ID column and multiply it by 2. So we're creating a derived column. You can do this with data frame API and with SQL, right? And I'm going to give it a new name, ID doubled, and then I want to pull out the user screen name. So this is the standard derived column syntax for a data frame. Okay, and we can do the same thing down here. What we're going to do here is we're going to say select TDS ID, multiply it times 2, and then select the user screen name one here. And we're going to do the exact same thing. And now the only weird thing is these odd column names. So why are we getting these odd column names? Like up here, we have reasonable column names. Down here, we get these _1 and _2. Why? Well, because the select, what is the type that this select is returning? Turns out it's a tuple. Tuple of type long string, right? So there's no column, there are no field names with a tuple. So it's got to use the _1 and _2. So how do we fix that? There are a couple of ways to fix that. We can cast, where everything lines up. So if I do a cast, let me clear all this stuff out. If I do a cast, then what it's going to want to do is line things up in order. So effectively, I'm going to say, I'm going to cast this over to this case class. I would like _1 to go into the first field of the case class and _2 to go in the second field of the case class. So I can do this cast, but it's really a compile time cast. I'm not going to get a runtime error. And in fact, if I get it wrong, it will complain, as I'll show you in a minute. Then there's another thing that you can do, which is called a projection. So instead of doing a cast, you can do a project. Now, in the case of a project, it's not order-oriented. Now, yes, the names are matched if you do this. So I'm going to take the original TDS. Okay, this is the one that has all the column names in it. And I'm essentially saying, I'd like to project this down to this case class. So effectively, it's going to match up the column names that are in the target case class and ignore all the others. So this is almost a way of just scoping down the type data set to just the fields you want. And in this case, order doesn't matter because it's doing a name-based comparison or name and type-based comparison. So this works fine. And because I've scoped it down to this case class, I've got columns, right? I've got field names, and so therefore I've got column names. But once again, if you get it wrong, you get compile time errors, right? So here I'm going to put them in the wrong order. This is the casting operation. So it should be long string because I'm going into this thing where the order is long string, but I flipped the column name so it's now string long. So what's coming out of here is a tuple in the wrong order, and I get a compile time error. Not the most readable compile time error, but you can figure it out. You get used to it. And here I'm going to do a projection, but I'm going to change this from user screen name to username. And once again, since it can't match the columns up, I'm going to get a compile time error. Right? And again, this all gets caught when you run your Circle CI or your Travis or your Jenkins job, which is awesome, right? And just as the final closing this out, here the names match, but one of the types is wrong. And so you're also going to get a compile time error, right? Which is pretty good. And again, compare that to the standard data set cast. Here I get an error, but once again, it's a runtime error. So your continuous integration compile is not going to pick this up. Now, what about some of the operations on the columns? Got 6 minutes. Can we do this? All right. I've been told I could run a little bit over. We might run a little bit over. So let's drop column ID and return a new typed data set. Now, you may have read that already. I'm hiding it. What's this going to return? What's the type? Type data set, the documentation for Frameless refers to this as the schema, right? What's the schema coming back or the type coming back from the select? Anyone want to guess? tuple, right? It's going to be a tuple. So we're going to get back a tuple, which means we're going to get weird column names again. Because doing a drop, notice it says drop tuple, that was your hint, right? You're dropping a column and it has to give you back some type that captures all the remaining columns, but you haven't given it an explicit case class type, so it's going to fall back to a tuple type, right? And then we're going to get these weird columns because tuple types don't have field names. All right. Again, you can do distinct. This is a pretty common operation to do. This works exactly as you would expect. Again, you're going to get weird column names back, but again, all the same operations you're used to are here. Aggregation is slightly less SQL-like. Okay, so one of the things you end up having to do here is use some temporary variables. If you don't have the temporary variables, sometimes Frameless can't figure out what type it has to infer into. So you'll notice here that if you tried to do this using the standard chaining, you're going to actually run into some problems. Okay, so I'm not going to walk through this too much. We're running low on time. But in any case, if you're willing to live with a few extra temporary variables, and what are a few temporary variables between friends, right? You get the compile time type safety you want, and you can do the full aggregation on this stuff. It's just a little bit more clunky than you might use with data frames. You can also use things like with column replaced to replace in place a value of a column. Right? And this because you're replacing an existing column with a new value for the same column, that it can retain the case class type, so you don't get the tuples back. You just get new values for that type, right? Which is really nice. What about adding columns? Okay, well, there are a couple solutions here. You can project. First, let's project this. We're going to do a project down to something more manageable. Too many columns in this display up here, right? Okay, so this gives me something that's actually a little more manageable. Not sure why I got this scheduled job up here. I'm not going to waste time trying to get rid of that. All right, so let's add a column. So what I'm going to do down here is I'm going to take some data, and I'm basically going to create a new case class that has a new column in here called ID, right? And I'm setting the value of that column to the literal 0. So you can almost think of this as a project up now. Instead of projecting down to a narrower data type, I'm projecting up to a slightly wider data type and applying the literal value I want it to be initialized with. And so if I do that, you'll see when you run this display that we suddenly have this ID column that's set to 0. And I can conditionally replace the column value. So here's a case where I'm going to take a particular screen name. And so that I'm not data sensitive, I've basically pulled the top screen name out of here already. And I'm going to say, filter it down, and then create a new data set where if the screen name is the first screen name, we're going to set the ID, we're going to propagate the ID as is. Otherwise, we're going to set it to a 1. All right, so you can see, oh, did I not run that? I may have dropped that out. I'm not going to put that in. All right, top screen name. Let's see if we can add that real quick. Top screen name. No, I don't have time to figure that out. We'll pretend that worked. Okay, what you would have seen if, I must have dropped that cell out of there. What you would have seen is that every single column is still a 0, except for that 1, right? And I'll put that in and correct it in the GitHub repository. But if you were to flip it, it wouldn't work. Okay, so this is, and I can't run this again for the same reason, but here you'll notice I flipped it. And the problem is it turns out this has an inference problem. It can't figure out where that lit is supposed to go. So you got to be careful. This would actually refuse to compile for a different reason, right? Even if I had top screen name defined. So this is a simpler way to add a column as well, right? This is the typical thing you do in Spark, which is select all the columns. So select star plus the ID doubled, right? And then we'll show 1. Well, this is how you could do that the frameless way. I'm going to select, now this is actually kind of interesting because it turns out to do something a little bit different. What the frameless one does is it actually takes the entire typed data set and makes it a new column. Right, and then adds a new column. So whereas the data frame select basically keeps it all flat all your original columns plus a new column at the end. The type dataset one says take all of the existing columns and make them one array column, right? And then add the new column so that, because to do the proper type management on it, right? So, you know, there are some syntaxes for how to drill into that, which we can talk about down here in nested schema. So the question is, what about performance? So let's do the join. This is our previous join, the same join we did before with the same screwed up filter in the wrong place. And one of the questions is, you know, is this thing actually doing lambdas? Am I paying a performance penalty to get all this type safety? And the answer really is that if you look at the explain plan, and if you were to compare this explain plan with the explain plan for the data frame version of this join, it looks substantially similar. There's the filter there at number 3, where it was before. Right? Now, it's comparing against this thing called Frameless lit. So there's some slight minor differences. But the plan itself, the execution plan, looks substantially similar to what you get out of data frames, not the problematic thing you get with data sets and, you know, lambdas. So you're still getting the same kind of performance that you would get if you stuck to the data frame API. Right? So we've hit 10:30. Let's see if I can blow through the remainder of this stuff in a couple of minutes. So how do I get, let's take a look at a nested schema here. We're going to pull this thing in. We've got a nested tweet data. So let's display it real quick. So once again, you notice I've got a row ID, and then I've got this structure type as the second column, right? So how do I drill into like the tweet hashtag in here or the screen name? Well, if you use data frame notation, it's dots. Tweet, I want the screen name, right? So you drill down with dot notation. Get it wrong, you get a runtime error. What you do in Frameless is you use this col many thing. So it's essentially saying, string these columns together. Take the nested thing, give me the tweet followed by the user screen name, right? So it's sort of, instead of using dot, you use col many. Now again, it's pulling back a tuple type. But the nice thing here is if I get it wrong, user screen nam instead of user screen name, I get a compile time error. So once again, I'm back to getting the compile time error. Pardon me. And then finally, there's this section in here we talk about jobs. So here's a job where I'm actually doing a take. Okay, a take is typically an action that will trigger something in the regular Spark. And so is a count. So in regular Spark, both of these things would trigger an action, but in Frameless, both of these things are jobs. And what I could do then is I can string those jobs together with flatmat, the same way you would combine any other monad, right? So even simpler, I can say, get me the count. Now that's a job, right? We haven't run anything yet. And then I'm going to do, this is a poor man's sample, right? Pull the first count divided by 100 rows back. Now it's not really a statistical sample, but I'm getting, you know, some 1/100th of the data set back. Yield that. Now this is going to give me back another job, which I can then run, right? And they can be combined in a bunch of different ways, right? So you can actually put them together quite simply with basic map calls, right? This example is very similar to one that's actually in the Frameless documentation. So the conclusion to this is, I'm not going to run this one. You can run this on your own. But the conclusion to this is then, I've got 3 APIs. Which one should I use, right? How do I start with this? What do I do? And your mileage may vary, but what I do is I basically say, if I got a hunk of data I've gotten from a customer or a client or, you know, even my boss, can you analyze this? I don't know what the shape of that data is. So I'm going to pull up typically a notebook or the Scala REPL within Spark, and I want to play with the data and figure it out, do some analysis of it, so that I can figure out, okay, what kind of production job can I run on this stuff? I'm going to use the data frame API there. Why? Because I can dot combine things really quickly. There's less to type, and if I'm doing that kind of analysis, I don't really care about runtime errors. I'm in the REPL. But when it comes time to write that production job, where I would really like to have the compiler protect me from doing stupid things, and in particular, protect me from making changes that break the job, now it's time to go to something more type safe. And if I want to go to something more type safe, my first choice is going to be Frameless, because it still compiles down to the data frame query API, so I don't pay any of those penalties. So that's my approach. Use data frames for the quick analysis, or Python if you really want to hurt yourself. But I mean, it's the same sort of thing, right? It's just deal with the runtime errors because it's fast, the turnaround time is quick, and then translate it all into something more type safe like Frameless. And you can do machine learning with Frameless. I don't have any time to go into that here, but there's a whole description out at the Frameless, what is it, typelevel.org/Frameless, I think is the Git book. There's a whole section in there about using machine learning APIs with Frameless, which can also help you. That's a little more problematic given the way the machine learning APIs are organized. But again, you get more type safety back without paying a performance penalty, which is a nice sweet spot that Frameless sits in. And with that, we're over time, so if you want to hit me up for questions, or if you want to ask the long cow here, the guy who can tell you all about how this is implemented, feel free. Meanwhile, that's it. That's data sets, data frames, type data set. I recommend playing with it. And this presentation, you can use that to play with it and go through the docs at typelevel.org Frameless. They're really very good. All right, thanks.